In today's video, we are going to be taking a look at the paired t-test in Python through a few different examples. We're going to go through a manual calculation and show you how some shortcuts in SciPy make your life way easier. But before we jump into the Python code, I want to go over a little bit more context of what is a paired t-test and when should you use it. All right, so let's take a look at the paired t-test. So the paired t-test can only be conducted with completed pairs. So you can think of things of like before and after. Probably the two most common ways that you're going to see this is in training or medicine. So the impacts of someone training, let's say for a race, or like what happened with users after taking a certain medicine. So the assumption here is that there's no other external factors influencing the outcome, and different pairs can't influence other pairs, right? They need to be independent of each other. Also, the paired t-test assumes that the data is going to be continuous and the difference is normally distributed. So if the data is not continuous and or the data is not normally distributed, you're going to be using the Wilcoxon signed ring test. I'm going to be covering that in another video, hopefully in a few weeks, right? So here's the steps that we're going to have to do. Number one, always pretty common on hypothesis testing, right? So state the hypothesis, alpha value, tail direction. Then calculate the differences between the paired observations, calculate the mean, calculate the standard deviation. Then we're going to check the normal distribution of the differences, determine the sample size. We're going to then calculate the T-Statistic, then determine the degrees of freedom, find the p-value, and draw a conclusion. 10 steps. Let me walk you through them, and then we're going to jump into some Python code. We're going to do one manual example also with this, and then jump into a lot of shortcuts. So let's take a look at Metallica sales. We're going to look at it before and after the Black album, and it's going to be a two-tailed test, right? We're going to have an alpha value of 0.05, and we're going to assume that these are going to be the same exact cities, right? So ticket sales before, this is the gross amount in dollars. That way it is going to be a continuous, right? And ticket sales after. So let's state the hypothesis, right? Alpha value and tail direction. So the mean difference in ticket sales before and after the Black album is 0. The mean difference is not equal to 0 since it's a two-tailed test. Step 2 is to calculate differences between the paired observations. So I have all the differences over here, right? Subtracted them, and then we get these down below: 300,000, 330, 330, 366, 357, 408, 399, and 447. Now we need to calculate the mean. So just add them up, divide by 8. Calculate the standard deviation, right? We get our standard deviation. Then we check for the normal distribution. We use the Shapiro-Wilk test, and we get a p-value of 0.892. So we don't have enough evidence to reject the null hypothesis of normality. I'm also going to be covering Shapiro-Wilk in another video, so don't worry about that one. Then we determine sample size, which is 8. Calculate the t-statistics. I get 21.43. Then determine the degrees of freedom. 8 minus 1, 7. This degree of freedom is super, super easy, right? And then find the p-value. P-value in this case is going to be very close to 0. And then since the p-value is much smaller than our alpha value, we reject the null hypothesis. This means there's a statistically significant difference in ticket sales before and after the Black album release. Look, that's not my favorite Metallica album. I like some of the earlier stuff, but it definitely helped them become mainstream. So with that out of the way, let's jump into some Python code. All right, so let's get started. What we're going to do first is import in NumPy and then SciPy. So import NumPy, then from SciPy, we'll import in stats. And that should be our only dependencies in this video. Now I'm going to set up an alpha value. So we'll say alpha equals 0.05. That way we have the same alpha value throughout the video. And let's take our first example. Now, this first example is going to be a manual calculation. I'll show you guys shortcuts later on, but I think it's important to go through somewhat manual example for the first one. So example 1, manual. And what we're going to take a look at is marathon times before and after a tough training block. So tough training block. We'll assume they run the same course. It's the same weather outside. And yeah, let's take a look at that. So what I'm going to do is we're going to have times before, and I'm just going to copy and paste my times I have here, and we'll have times after. So 240, 250, 245, 55, 30, 235, 260, 265, 228, 242, 235, 250, 233, 225, 253 and 264. Import NumPy as NP. I apologize. That's why it wasn't registering here. And we have both of these over here. Awesome. Now what we want to do is we're going to find the differences between both these. So we'll say differences equals. And what we're going to do is we're going to have times after. We're going to subtract that from times before. So we can see overall how well people performed. So let's take a look at these differences first. So I'll just print out these. Print differences. And we'll see -12, -8, -10, -5. So all these people improved. This person got worse. These improved over here. Hold on. 1 minute. If they weren't running 4-hour marathons, would be not a horrible improvement, but yeah, not the best, going from 265 to 264 minutes after a training block. All right, and let's now calculate our mean and standard deviation. So we'll say mean diff over here equals np.mean. Then we'll pass in these differences. So pass those in over here. And yeah, let's print this out as well. So you can see what the mean is. And overall, right, about 6 minutes, which again, not the best, especially being a 4-hour plus marathon, but it's progress, right? And what we want to do now is calculate the standard deviation. So we'll see std diff equals np.std, and we'll pass in differences like that. And let's see what the standard deviation is. So, and actually I did make one mistake. Let's put DDOF equals 1. So DDOF equals 1 because it is a sample that we're taking a look at. So let's grab that and we'll print that out. So print out standard over here and I get 5.06. All right, now we need to test if this is a normal distribution. So what we're gonna do is the Shapiro-Wilk test, and we'll say stats, and we'll have our Shapiro p-value. So Shapiro p-value like that. We're gonna say equals stats.Shapiro, and then we'll pass in differences like that. And then we'll print this out, our p-value, and we'll have it greater than 0.05. And you can see it's 0.43. So we are good to assume that this is normally distributed. I have a full video on Shapiro as well. Okay, now what we need to do is calculate the length of these differences. So n equals length over differences. All right, so we have that over here. And let's also calculate our T-Statistic. So our T-Statistic equals mean diff divided by std diff divided by np.square root. Pass in n. Great. And now we have all of those. Now let's calculate our degrees of freedom. Well, let's print out our T-Statistic first. And then we'll go into our degrees of freedom. So you can see it's -3.49. Then let's calculate our degrees of freedom. So df equals n minus 1. Super easy, right? And now let's find our p-value. So we'll say p-value equals 2 times, and inside over here we'll have 1 minus stats.t.cdf. So over here, absolute value, pass in our T-Statistic, and then pass in df. All right, and then I'll get our p-value. Again, only one time we're gonna have to go through this manual process. And what I like doing is having an if-else statement over here. So if p-value is greater than alpha, there's no difference in before and after times, else the difference between is significantly different, right? And the before and after times are significantly different. If you take a look, right, -12, -8, -10, -5. I mean, most of these people improved. One person did not really improve. So awesome. That was our manual calculation, but really, we can make this way easier. Let's take a look at example 2. And example 2 is going to be a Metallica ticket sales example. So we'll say Metallica ticket sales example. And we're looking at the revenue from the ticket sales, right? So let's grab our ticket sales before, and we have this over here, right? NP array, And what do we have? We have 240,000, 270, 255, 264, 258, 252, 246, 243. And then what we'll have is ticket sales after. And for this example over here, we'll take a look at the Black Album, and we'll see the differences between, before they released the Black Album and then after. And I can't remember if I mentioned this in the slides or not. Black Album is not my favorite Metallica album, but it helped them go mainstream. So have that over here. And then like before, right, we can find the differences. So what we can say is ticket sales diff equals ticket sales after minus ticket sales before. I guess I should have just copied those. Been quicker than typing it, right? And we can print this out. So print out our ticket sales diff over here. We have all of those. Awesome. And then what we want to do on this side of things is do our Shapiro. So we'll say stats, and then we'll have Shapiro p-value. That's going to be equal to stats.Shapiro, and then pass in the ticket sales diff. Great. And then let's print out our Shapiro p-value. Again, we want to have this greater than 0.05. It's 0.89. So we're looking good over there. We know normally distributed. And now we can do the t-test over here. And all we have to do, super easy. We'll say T-Statistic. We'll have our p-value equals, we'll say stats.t-test rel, and then pass in both of these. So we'll have ticket sales after and before. Right. Put those, and instead of subtract in here, put a comma. Right. Now we have both of those. And what we can do is we can print out both of these values if we want. I care more about the p-value because using that, and you can see the p-value is very, very close to 0, right? And let's print out our if-else statement. If p-value is greater than alpha, there's no difference between before and after Metallica ticket sales. And if it does not fit this, which it won't because we have a p-value close to 0, the before and after ticket sales are significantly different. The before and after ticket sales are significantly different. Metallica got a lot more popular from the Black Album. All right, and let's take a look at some one-tail examples. So this is going to be example 3. Example 3, we'll look at a right one-tailed, and we're going to look at the impact of a new hitting coach. And we'll assume that there's going to be like 9 hitters for a baseball team. Technically, there'll be more, but here's our batting averages. We'll have 250, 240, 260, 270, 265, 255, 250, 245, 260, and also 270. So that's our batting average before. Now we'll have our batting average after, which we'll have over here, right? 300, 290, 310, 320, 305, 315, 290, 285, 315, and then 325. Okay. Then we want to do our Shapiro test again. So we'll say batting average differences. So batting average diff equals, and then we'll have after minus before rates. Oops. And actually, I messed this up. I need to put np.array here. And then I'll do that for both of these over here. Right, now this will work. Great. And let's just make sure that this batting average difference is normally distributed. So we'll say stats, we'll say Shapiro p-value, and then we'll say equals inside over here, stats, Shapiro, then we'll have the batting average diff. Great, let's print out this p-value. So print. Again, we need this to be greater than 0.05. Hopefully it is 0.11, so barely makes it. Well, I wouldn't say barely, but yeah, we're good to keep moving forward. Then what we're going to do is, again, kind of just copy the same code that we have over here, right? And I'm going to make one modification. We'll say p-value, and we're going to just mention that this is two-tailed. because we are looking at one-tailed, we're going to have to change this up a little bit. So what we're going to have over here is batting average after, and then batting average difference, right? And okay, so we have all this over here. And then what I like using is this code on this side of things. So we'll say p-value one-tailed equals p-valued, two-tailed divided by 2 if our t-statistic is greater than 0, else 1 minus p-value divided by 2, right? So that determines left or right tail. And then we can have our if-else statement. Right. So if p-value is less than alpha, the hitting coach had no impact. Else the hitting coach had a positive impact because we're looking for the team to do better, and they did perform better. And you can take a look over here: 250, 300, 240, 290, 260, 310. I mean, these are huge improvements in baseball. Really, really big difference in between both of them. So that's our right tail. And then lastly, let's take a look at a left tail example, which is the impact of a worse baseball. And we're going to take a look at home runs of different players. So a few years ago, Major League Baseball dampened the baseball, so they made it a little bit worse. Although I think that's changed, but we'll look at that. We'll say left one-tailed impact of worse baseball. And all right, so let's pass in our home runs before, and we have all these over here, and then we're gonna pass in our home runs after, right? So season before, these were the home runs for some of the best power hitters. This is the results for the season after the baseball change. Again, we have a worse baseball. And what we want to do is calculate the differences. So what we'll mention first is we'll say like home runs difference, that's, and we're going to say that's equal to home runs after minus home runs before. So home runs after minus home runs before. Let's do our Shapiro test. So let's grab this over here, and then we'll just pass in our home runs differences, right? So we have that now. And then what we can do is print out our p-value. Now, hopefully this is, again, greater than 0.05, right? And you can see it's 0.11, good to go. And then now what we want to do is get our two-tailed p-value. So we'll pass this in over here, change this up. So we'll have our home runs after and home runs before. So let's pass in those. So home runs after, then our home runs before. This is great. We have that now. And then let's take a look at our actual p-value, because this is two-tailed. So again, we'll have p-value one-tailed over here equals p-value divided by 2, right? Same exact stuff. And what we can do now is have our if-else statement. So I'm going to go over here and change this up a little bit. So we'll have p-valued one-tail, which I just realized, by the way, did mess this up because I forgot to put p-valued one-tail. My bad. It's going to be the same result, right? Because that p-valued is going to be pretty low. I didn't even print that out. So I apologize for messing that up a little bit above. I just noticed that, but regardless, let's see what our actual p-value one-tail is over here. And our p-value one-tail is essentially 0, right? So instead of the hitting coach had no impact, we'll say the baseball change had no impact. And then the difference is the baseball change led to a smaller amount of home runs, right? And let's take a look at that. Right, the baseball change led to a smaller amount of home runs, right? We saw differences over here. We went through the whole testing process. And yeah, I mean, honestly, it's pretty easy, this side of things. And if we went through the manual process, it is a bit of work, but SciPy makes it really easy. So what I recommend is doing your Shapiro test to make sure that there's normality. And then all you have to do is stats.tTestRow, get and just post in after and before. The only difference is if you're going to look at one-tailed or two-tailed. If you look at that side of things, you're going to have to add in one more line of code because The p-value they give you by default is two-tailed, so you have to change that up, and that depends on the value of your t-statistic and as well as the test that you are currently performing. But yeah, that's essentially it for this video. Hope you guys found some value from this video, and if you learned something new about the paired t-test, make sure to subscribe to the channel. We're trying to reach 100,000 subscribers in 2025, and the way we do that is by uploading at least 3 videos every single week. Now, if you want to learn even more about statistics, I have a playlist linked down below, as well as a few videos that I think you guys would like, but you could also click right over here to jump into it.